Bayesian class estimation and R.
Le micro, ouais.
It's my pleasure to introduce our recent work on Bayes class estimation from high angular resolution diffusion unity. This is a joint work with my student Jia and my colleagues a minute ago from National University of Singapore. So I will show you in this talk that this is an application of information geometry in medical image analysis, and particularly we want to study the brain white matter anatomy using information geometry theory. So this is a postmortem, pictures of the brain, and you can see the white matter regions of the brain is packed with axons that connect the brain regions from one to another. So advanced, diffusion-weighted magnetic resonance image allow us to monitor a water molecule motion in the brain, and such that this information can be used to characterize a distribution of axon orientation in the white matter. And the simplest, the model for monitoring water molecule motion in the brain is a diffusion, Gaussian diffusion processes. So the picture down here basically encodes the Gaussian tensor models that allow us to characterize predominant axon directions in the white matter. However, the brain axons, in the white matter is actually is quite complex, has a quite complex organization. And 2/3 of the white matter regions actually have crossing fiber regions, which cannot be characterized using a single tensor. So recently, researchers has extended this tensor model to what we call the free model, which is the orientation distribution function. And this orientation distribution function is a probability density function defined on the sphere. The figure shown here just illustrates what axon could look like in particular region. So here the color information as well as the shape information encodes the same information that tells you where the axon is oriented in the brain in this location. So now the question is, given our observations, a number of subjects, we not just have an orientation distribution function at each spatial location, but we also have anatomical difference, global anatomical difference across subjects. The question is how we will use such information to build a kind of an image atlas that represents a white matter anatomy across individuals. So the focus of my talk is to first discuss how to study the distribution for orientation distribution function, ODF, in a Riemannian manifold. And I will then introduce a Harding atlas generation approach with decision theoretical scheme based on Bayes modeling. So let's just look at the orientation distribution function first. So we can define a space P, and that is a probability. It's a set of probability density function defined on the unit sphere. And from information geometry, this space actually forms a Riemannian manifold with a Fisher-Rao metric. It depends on how we characterize this space, and the Fisher-Rao matrix can be written in different way. So here, we particularly use the square root for ODF as a permutation of this manifold. And psi x here is equal to square root of ps, and capital psi here is the space of psi that defined in the unit sphere. And this space actually forms a part of a unit Hilbert sphere. The inner product can be written easily as the L2 norms, where epsilon j and epsilon k are tangent vectors at the psi I location. And in additionally, using this square root ODF representation, we also have an analytic formulation for log map as well as exponential map. So the log map is actually can map the tangent vector epsilon back to the manifold space I'm down here, while the exponential map can map so the log map actually can map the tangent vector at location, can map the elements in the manifolds back to the tangent location, the tangent space for a particular location, and exponential map can map the tangent vector back to the manifold location. So we have all these analytical forms for computing a log map and exponential map. And particularly, we also can compute the distance between the ODF in this manifold. It's basically just angle information between the two. The Kershaw mean among set of ODFs that can be computed using this minimization problem, where the distance is defined in this equation. So now let's see, how we will be able to build a probability density function on the ODF such that we will be able to study the mean of this. So the way we build it is to look at, the way we do this is to look at probability models in the tangent space at particular location in this manifolds. So epsilon here basically gives us a linear representation in this tangent space such that we can assume epsilon is centered as a Gaussian field with some covariance sigma square and gamma. And gamma here, we particularly choose an identical operator to be consistent with the inner product I showed you previously. So hence, the probability probability density function for a particular sign probability density function for ODF information that near to the sign I location can be written as a form down here where the Z is the normalization terms. And from here is the distance metric we showed you previously. So now let's see how we will be able to embed this probability model of ODF into the framework of Bayes modeling, while we also need to incorporate spatial differences across individuals. So here our observation is individual ODF images in 3D space, and at each location we also have ODF functions. So the question is how we will be able to build an atlas. So the way we do this, we basically assume there's some hyperatlas we know, and we can actually deform this hyperatlas through some transformation, which is we call phi, and the atlas we want to estimate can be equal to phi x on the hyperatlas we know. So in order to link the estimates and our observations, we basically introduce a series of hidden variables, which is the transformation that allow us to approximate individual observations as a group action of phi on the atlas, which is shown down here. And of course, based on previously what I introduced, here there's also, this is only saying the observations we have can be centered around the region, which is phi I composed with I atlas. And there's variations that can be characterized using sigma parameters we showed you previously. So here, the bottom line is we need to estimate parameter for phi, which is how the hyperatlas will be able to deform such that this atlas will be able to represent to the observations we have. And we also have the sigma parameters that characterize variation for the data we observe. So give you a more mathematical formulation. So here, given the observation of a series n number for ODF images in R3 space, and we also know the hyperatlas, which is I0. So we can write a posterior as f theta, which is phi given our observations and also the hyperatlas. Its maximum can be found using expectation maximization algorithm by first compute a log likelihood function of complete data, which is phi and phi I for individual subjects deformation and Ji of our observation in the form of the following down here. So which is we can write as this is information related to the prior information of the atlas, and this is log likelihood related to the deformation, and this is log likelihood related to the ODF information. Based on previous introduction on the probability model of ODF, we basically can write our conditional log likelihood for the ODF function can be approximated as the following equation, where here x down here is the spatial domain of R3. So we basically assume at individual vectors they are independent of each other. For the shape model, we basically based on our previous work. So we basically assume the atlas, so the hyperatlas can be deformed to the atlas we want to estimate through a diffeomorphic transformation. And such diffeomorphic transformation is created, through a flow of diffeomorphisms. And this path that connecting to the two objects has to be shortest. The length of this geodesic curve is defined as the remaining length of phi t, computed as the integral of the norm of velocity field, as what I showed you down here. And capital V here is the Hilbert space, and that associated with the Hilbert space of the smooth vector field, and that can be controlled for the smoothness of the Vt. And kernel Kv is corresponding to the kernel in the Hilbert space. We can have an alternative representation for this non-computation. Basically, we can use the dual isometry in Hilbert space so that we can show the norm of Vt in the Hilbert space can be written as Kv mt times Kv mt in the product is mt in the L2 space, where the mt here is the time-dependent momentum. Based on previous theory, basically under this construction, so this geodesics that connects to the hyperatlas with the estimates can be computed through initial momentum. We don't need to know the time-dependent momentum along the trajectory. We basically only need to know the initial momentum, which is located in the hyperatlas space. So this is a very nice theory, such that given an initial momentum, one can generate a unique time-dependent diffeomorphic transformation. Hence, the space of the initial momentum provides a linear representation of a nonlinear diffeomorphic shape space, in which a linear statistical analysis can be applied. So, using an initial momentum, we basically can model the shape prior. We basically assume M0 to be a centered Gaussian random field, and the distribution of M0 is characterized by its covariance by linear form defined in this equation down here. And V and W is basically is velocity vectors in the Hilbert space of V. So we basically associate this covariance by linear form with the kernel inverse, which is consistent with our diffeomorphic mapping. So we basically assume this parameter is known. So thus, the diffeomorphic atlas shape prior can be approximated as 1/2 inner product of M0 and Kv M0 in the ultra norm way. So similarly, we basically can construct the log likelihood function for the deformation components in the similar construction as what we show in the diffeomorphic atlas shape prior. So we can basically say, the log of likelihood for deformation can be approximated as 1/2. I should have minus sign here. So M0, I compose Kv pi. Particularly, this correction matrix can be different from the shape prior we use. To integrate all together, so the biggest modeling we have right now is basically the first component to show you the shape of prior information for the atlas, and this component basically show you the log likelihood function for the deformation, and the third portion basically is log likelihood function for the ODF information. So here the atlas is the transformed hyperatlas information, which we can compute it through differential transformation. So in order to solve this problem, we basically employ expectation maximization algorithm. So I can show you step by step how we will be able to compute that problem. So in the E step, we basically compute the expectation given the estimates. So as you see here, so the first component for the prior information is nothing to do with expectation, while the second component down here, we basically assume the atlas is actually centered along the observation such that expectation will be equal to 0. And the third component down here for the log likelihood function of ODF, which is the expectation we need to show. We basically can easily compute this one if we assume psi 0 bar. Psi 0 bar is a sample, the mean that can be computed based on the individual observations. And here, it basically d phi I here is the deformation. So this is a kind of a weighted average of ODF function in the remaining framework of ODF, space. So this is can be directly computed using a gradient descent method to estimate what is this psi 0 bar. And to give you an intuitive illustration, so this one basically says that if our current mean is far from particular individuals, so in the next iteration, so the deformation down here will be larger. So basically we will weight this individual subject more as we compute the mean. So we can simply see in the maximization step, we can simply show sigma square, which is the tertiarized variation of ODF at across the whole space can be computed in this equation. And down here is mean variation on ODF information, and we integrate across the space, and we also compute it across individual subjects. So the initial momentum that allow us to deform hyperatlas to the estimates, and basically we can estimate this through this minimization problem. And this is a typical problem called large deformation diffeomorphic metric mapping problem, and particular adapt to the ODF images. So I'm not going to talk about how we solve this problem, but refer to our references shown down here. So in practice, how we will be able to compute this? So the first step what we do is we initialize the atlas. We assume atlas we know. So we basically use large deformation diffeomorphic metric mapping for ODF algorithm to map this atlas to individual subjects. Then we basically, in the second step, we basically compute this psi 0 bar through gradient descent method, and then we will be able to average ODF based on its deformation as well as the shape of ODF across individual subjects. So the third step, we basically update the sigma square using the equation I showed previously. And the first step, we basically solve this mapping problem that allow us to deform this hyperatlas to the estimates we want to compute to this psi 0 bar, and the final atlas can be approximated as the deformed atlas through this initial momentum. To illustrate how this psi 0 bar works, so basically this is in the initial step, so we basically can compute this psi 0 bar. You can see the y-vector mapping is very, very blurred. As during this optimization procedure, you can see we can gradually recover detailed information of the y-vector. So finally, I'm going to just show you briefly one of the results we have for using this approach. We basically generate aging hardy atlas using 200 subjects, aged from 22 and above. And as you see, in this crossing fiber regions, which is in the box of green, and you can see we can still remain the sharp structure in these crossing fibers regions. While in these sharp regions where you have post-closure regions, you can still, in this atlas generation approach, we still remain very sharp information, which is unique single bundles crossing the post-closure structures down here. To summarize, I basically introduced a Bayes framework to compute the atlas for the white matter